Salam et bonjour. We believe we have moved beyond the question of whether or not the machine can compose decent music. The question today is whether the machine can really become a virtuoso, and if yes, how, to what cost, and when. In this contribution, we try to answer these questions in the context of maqam music. So welcome to the presentation. Let me start by the outline. I will firstly give a brief introduction to maqam music. I will then discuss responsive melodic accompaniment as a machine translation problem, and finally comes the evaluation, objective, subjective, and user study. Music in the Middle East and parts of North Africa is based on the concept of maqam. It is a set of pitches, characteristic motives, and formulas of their use. Each maqam has a well-defined character that's recognized by the knowledgeable listener. And when it comes to automatic processing, maqam music is challenging. There are about 10 main maqamat in Middle Eastern Arab music, with possibility for microtonal deviations among regions. Further, the smallest quantization steps the quarter tone, which is challenging for pitch detection, especially for low-pitch expressive performances. Also, there's a lack of available transcriptions. And when it comes to performance, there's an elaborated freedom in interpreting simple melodies, usually performed in a heterophonic structure. Now let us present briefly the Arab vocal improvisation. Mawwal is a traditional form in Arab music. It consists of several poetic verses narrated over an improvised melody in a particular maqam. It is non-metric, tightly connected to modal ecstasy or tarab. And here's an example of Mawwal.
زدني بفرط الحب فيك تحيرا زدني بفرط الحب فيك تحيرا
In our work, we focus on responsive melodic accompaniment to Mawwal and imagine it as a machine translation problem. So each vocal idea is considered as a distinct sentence, same for instrumental responses. Now, to reduce the size of the vocabulary, we use the scale degrees and quantized durations rather than pitch and durations. We then use textual symbols to represent them, just as shown in this table. Phrase-based translation involves creating a lexicon of parallel phrases and calculating the probability of each possible translation for each phrase. Then for a new sentence, we search for the translation that obtains the highest score. We built our own corpus. The keyboard emulates Arab instruments to a sufficient degree, and when using MIDI, retrieving pitch and duration is very accurate. We also retrieve vocal melodies automatically, but while controlling the settings, mainly maqam and quietness. We expanded the corpus over 3 stages. Let us pass briefly by some corpus statistics. In this table, I am mostly interested in spotting the light on the overall length of recordings. More than 23 hours. Each hour here means several hours in our recording rooms. Now this table presents statistics on the sentence level. See how wide the range when it comes to the length, from 1 note to 90 notes for vocal, and almost double the range for the instrumental accompaniment. And when it comes to the count of parallel sentences per maqam, the range is between 1300 in Ajam and 400 in Huzam. Here's an example of a human and computer translation for a given vocal sentence.
أمان 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 يا أبا
We also found it interesting to publish an artwork based on this model. Let us listen to a few sentences.
ترقب إذا جن الظلام زيارتي إن غبت لم ألقى إنسانا يؤنسني أضحى الثناء بديلا عن تدانينا إن الزمان الذي ما زال يضحكنا أنسا بقربهم قد عاد يبكينا
Now let's talk about the evaluation of the model. We will start by the objective evaluation. We use the bilingual evaluation under study, BLUE. It's a measure used to estimate accuracy of natural language translation. In the expansion from 2.8K to 4K, the score decreased from 18.8 to 17.7, possibly because of introducing new musicians. From 4K to 7K, however, the score increased from 17.7 to 22.1, indicating a considerable rise in quality. It's good to mention here that no new musicians were introduced in the last expansion. However, we feel the quality of translations steadily improved across expansions. We therefore found it useful to apply subjective listening tests. We conceptualize virtuosity within the context of tarab, modal ecstasy, which does not privilege technical dexterity in the same manner or to the same extent as Western European aesthetics. In tarab, performers are often appraised for deftness in improvisation, mastery of maqamat, their path and modulations, also relating text to melody, as well as complexity and appropriate modulations, and physical production of sound. Actually, tarab refers to both a form of emotional response and a set of aesthetics, emphasizing slower tempi, repetition, etc. Tarab involves layers of interaction between the singer, instrumentalist, and audience, which A.G. Rassi terms an aesthetic feedback model. This approach allows us then to explore the culturally contingent complexities of a human-computer interaction, and specifically the role of a computer interactant in an Arab music setting. We use the Mawwal computer application to create listening tests and further examine its functionality in a user experience interview. We replaced the application's rule-based accompaniment with a statistical machine translation model. The application retained the original Mawwal vocal transcriber that was also used in building the corpus. For listening tests, we fed each vocal sentence into the model individually and exported it together with its instrumental translation. For the experience interview, a musician experimented with the application directly through this graphical user interface. Now let us talk about the listening test experiment settings. 3 evaluators, all professional practitioners of Arabic classical music, listened to 100 parallel sentences, each translation rated into one of 5 ranks. We ask evaluators to consider pitch and rhythm. The following table presents the results, and further discussion is to follow. The figure presents a preliminary equation that represents the relationship between corpus size and subjective results while assuming a logarithmic pattern. It seems that the corpus size needs to increase to 18K in order for human and machine accompaniment to be comparable. When it comes to perceived equality versus sentence length, and as shown in the figure, the quality increases with length in human translation, the blue color, and decreases with length in computer translation, the red color. For human translations, long sentences were possibly considered more melodically complete, leading to a deeper sense of tarab and more mature responses. For computer translations, quality decreases with long sentences, as those usually have complex melodic paths. Interestingly, the machine outperformed the human for very short sentences. Those are often used within a quick, highly interactive call-and-response exchange, where the instrumentalist may alter the performer's expectations. When short, human-translated sentences are removed from the performance context, evaluators may perceive translations as disjoint. Our model design does not consider previous sentences as a human performer would. we noticed what seemed to be an interesting pattern of evaluators' disagreement. So we decided to investigate the relationship between the perceived equality and evaluators' disagreement. We considered evaluation data from the automatic accompaniment over 3 different corpus sizes, as well as those of human-performed translations. The relationship between perceived equality and inter-evaluator disagreement tends to follow a higher degree polynomial function. It suggests that with further corpus expansion in size and quality, which will also lead to better automatic equality, disagreement is expected to rise gradually until reaching a maxima when the average equality is about 4.7. For future corpus expansions, we either focus on higher quality while accepting more disagreement among evaluators and the broader music community, or accept lower equality as well as lower disagreement. Let us discuss now the user study. We interviewed Mawwal Al-Khatib, a professional vocalist and oudist who extensively used this model, including a performance in published musical artwork. Of a primary concern was whether this model can elicit or has the potential to elicit tarab. Mawwal's framework for assessing audience engagement was remarkably different from the shouts, gestures, and gasps that scholars typically note as indicative of tarab. He pointed to smartphones as significant to interpreting audience feedback. I quote, "The more mobile phones are recording, the better the work is. Although it is a contradiction because I want them to listen, but still, it is nice." Unquote. This suggests that contemporary technologies have already come to reconfigure the performance and the experience of tarab. In Mawwal's view, the model allowed to concentrate more fully on his own performance, even bypassing the need to interact with other musicians. The lack of interaction, however, prevented the cultivation of modal ecstasy, as it lacked the spirit and the expression of feelings. He did concede, however, that he at times loses ecstasy when performing with the human musicians, when they too do not correctly demonstrate feeling and attention. Mawwal admired the machine's processing speed, tuning, and successful recruitment of vocal intervals and instrumental responses. He said this supports modal ecstasy. On the other hand, he disapproved when the machine sometimes altered the direction of the melodic path. Mawwal gave suggestions for an improved experience. He requested a drone along with the vocal sentence, which would imitate a standard Arabic music practice and provide a stable reference pitch. He also recommended offering different regional accompaniment styles, such as Egyptian and Iraqi. He argued that every Mawwal has a spirit, similar to the spirit of law, that must be intuited. Mawwal's suggestions may help the model further integrate into or reconfigure the tarab feedback model. There remain, however, a number of limitations. The machine may constitute another form of distraction for audiences. However, Mawwal noted that he was not distracted as a performer. The model may challenge musicians and audiences to fundamentally reconsider what exactly constitutes spirits and feelings in performance. Where are spirits and feelings found, whether in musical content, performance atmosphere, or the presence of a performing human body? So it remains to be seen whether machine participation can imitate, produce, or reconfigure spirit and feelings, and whether audiences and musicians will allow for machine participation to modify and extend the tarab feedback model. And here comes the conclusions. We worked on predicting and critiquing machine virtuosity in the context of Mawwal. We extensively evaluated the melodic responsive accompaniment model based on statistical machine translation with objective and subjective approaches. Unlike subjective listening tests, the objective measure, BLUE, was less consistent in assessing music translation over a series of corpus expansions. BLUE, however, remains a useful indicator when testing corpora with larger differences in size. By focusing on subjective evaluation, we were also able to predict translation equality across corpus expansions. Our discussion highlighted the importance of examining cultural and social context when developing accompaniment models. We considered machine virtuosity within the context of tarab, interaction, and attention, which allowed us to further attend to performer and audience expectations in a specifically Arab music context. This holistic and interdisciplinary approach afforded new and at times unexpected insights into this ongoing research. It is also helpful for understanding how machine virtuosity may reconfigure the sociality of music making. Thank you very much for your attention.